Good morning, everyone, and welcome to the ARMA Student Design Competition final presentations. I'm going to pass it over now to Christian for the introduction.
All right. Good morning to everybody. We would like to thank you all for being here and support this initiative and the finalist teams for this competition. Welcome to the ARMA Student Design Competition with the final presentations. This competition was sponsored by Itasca Consulting Group, the American Rock Mechanics Association, and the University of Kentucky College of Engineering. The organizers of the competition of this year was the ARMA student chapters are Virginia Tech and the University of Kentucky. So the objective of this competition was to involve students from rock engineering related programs in a slope stability problem. They were asked to submit the best solution, including an engineering design to solve the problem. Here we have some highlights of the competition so far. So this is the first student design competition hosted and organized by the American Rock Mechanics Association. As a part of the competition, we organized a webinar given by Dr. Lorik from Itasca Consulting Group that it was held on April 9th. He basically taught how to use flag slope software for the slope stability analysis. We have more than 160 attendees, and right now this video is posted on Itasca YouTube channel with more than 1,000 views. In the first phase, we have the registration of more than 40 teams from 29 universities and 17 countries. For the final phase and for the submissions, 21 teams submitted a final report, and we have more than 2,300 prizes for the top 3 winners of the competition. So now I would like to introduce Dr. Lorik from Itasca Consulting Group for some opening remarks.
Thank you very much, Christian. So this is a really great pleasure for me to be involved in this particular ARMA project. It is, as Christian said, the first attempt at this, and we hope to make this an annual event. And so thanks to everyone for being sort of guinea pigs in this experiment. Just a few other comments that we hope to be able to distribute back to each of you comments from the judges on your submittals, as well as distributing at least the final selection, or maybe the top 2 or 3 selections to everyone, so you can see their submittals and maybe learn something from that. Hopefully this has been a learning experience. And I know for myself, I count every day that I learn something new as a good day, and hopefully you learned something in this process. So next I'd like to introduce the judges who will be involved and have been involved in evaluating the submittals. You can see them up on the screen here. Emmanuel DeTournay from the University of Minnesota, Paul Young from the University of Toronto, and Mark Diedrichs from Queen's University. Antonio Babbitt unfortunately could not join us today, but participated in the selection of the finalists. So I'm very grateful to all of the judges. And finally, Peter Smealy, the executive director for ARMA, could also not join us today. He had a personal conflict. So I think it's best now if we get right to the presentations. That's the focus for today.
Okay, thank you, Dr. Lorik. So as we said before, we had in total 21 submittals, and the panel of judges selected 6 finalists for this round, for this final round. This year's competition are the University of Dakota Crazy Hawks from University of North Dakota, Geotechnical Engineering Peruvian Advisory from Universidad Nacional de Ingeniería, LMR Consulting from Laval University, Stabilizers from IIT Dambad, Manic Miners from University of Belgrade, and Veteran Endeavor from UPN Veteran Jakarta. So we would like to congratulate all the finalists, and I think we're ready to start with the first team, UND Crazy Hawks.
Good morning, everyone. We are the UND Crazy Hawks team, and we will be presenting our slope analysis and design for an open pit mine. This is our agenda for the presentation. I'm going to go through the first couple slides a bit quickly, as it's mainly just the background information. The problem asked us to design a stable slope given the geotechnical data. We used the flat slope software and designed based on a factor of safety of greater than 1.3. The financial criteria required that the income be equal to the cost. We used the mean rock mass property values for our main design. We could have chosen to use a more conservative values, but we decided to address the material variability using a sensitivity analysis, which we will touch on a little bit later. The main assumptions were given to us in the problem statement, but we made a couple extra ones ourselves. So one of them was that the host rock extended out to an infinite width. That meant that we could make our model as wide as we needed to be. The other assumption was that when the site workers dewatered the groundwater table, they would match the design exactly, even though that's highly unlikely in real life. Our slope design main assumptions were mainly made to make the financial calculations easier. So both the ground and the groundwater table slopes were at a constant angle, there were no benches, and a flat bottom surface. The base of the mine pit was 100 meters wide, which meant we could excavate all of the ore to that final depth. We did not account for local instability, and we modeled 2 slopes in flat to account for any surcharge effects that the opposite slope would have. Our overall approach pretty much consisted of gathering up all the data, putting it into a geotechnical model, and then creating that 2-slope model in flat. Initially, we did some basic trial and error, and we realized that we could not make the model greater than 600 meters while also satisfying the financial criteria. So after that, we created this cost function and slope optimization program, and we used that to design a whole bunch of designs between 400 to 600 meters depth. And starting with the shallower depths, we modeled them in flat, and eventually when we hit 540 meters, that's when the factor of safety became less than 1.3. But we realized that the pore water pressure had a much greater effect on the factor of safety than the slope angle. So rather than giving up at that depth, we decided to change the groundwater table design, and eventually we got a suitable design. So the details of this cost function and slope optimization I mentioned will be presented by our next presenter.
So the methodology we have used in this problem is different than the common ones. Since the goal of this problem is to find the deepest depth where the cost equals the income, we thought of turning this problem into an optimization one. Thus, we built a cost function based on the cost and the income. As you can see in the slide, the income is in function of the excavated depth x, as you can see in the sketch, and the dip angle of the slope, which is A1. The dewatering cost is in function of the water table y and the angle of water removal A2. All parameters are illustrated here in the figure, where the red part is the ore. With 4 variables, the excavation depth x, the excavation slope angle A1, the water table level y, and the dip angle of water A2, made solving this problem complex. And we cannot use a linear solver for this, so because it contains many local solutions and global ones. Thus, we have hand-coded a stochastic optimization algorithm called Gray-Wolf algorithm, to optimize the cost function in Python. The algorithm starts by generating solutions, then these solutions converge to different optimum ones. And there was the start of our analysis. So the generated result have been used as the starting point for our trial and error process. You can go to the next slide, where we have modified the generated results from the algorithm to get more depth. At the same time, worked on assessing the financial result from the modified design. The result that we have obtained is an excavation depth of around 540 meters with a slope angle of 53 degrees, a water table of depth of 560 meters and an angle of 40.8 degrees. The resulted FOS is in the order of 1.322, which is accepted in the context of the problem statement. The financial analysis is illustrated in the slide per meter length. We can see the excavated surface from the array, the total excavation, and the dewatering area. The cost was calculated for dewatering and excavation, then compared to the income, which are similar for the recommended design.
The recommended design introduced by Ahmed was based on mean value of rock mass strengths, but in reality, the rock might be weaker or stronger at different locations. To check the effect of variability of rock mass on the factor of safety, we did the sensitivity analysis. Based on the provided coefficient of variation and mean value and the formula located at the right side of the slides, we can get the standard deviation for friction, cohesion, and tension at each layer were calculated. Based on the normal distribution, there are about 36.6% possibility that the values locate between the mean minus standard deviation to mean plus standard deviation. And there are about 90.8% possibility that values locate between mean minus double standard deviation to mean plus double standard deviation. And the values calculated by this method are used for the sensitivity analysis. And next slide, please. And from the deterministic analysis method, we can check the variability of cohesion, friction, and tension. And these three figures shows the FOS change based on the rock mass strength value deviation from the mean value. And we can see that the change in tension doesn't make a significant difference to the FOS. Actually, FOS is more sensitive to the change in cohesion followed by friction angle. If we see the figure of cohesion, the solid line is for all three layers change values simultaneously. It is possible that a significant overestimation of cohesion in all three layers may lead to the slope have a lower FOS, which is smaller than 1. However, that is an extremely unlikely case, and for most of the overestimation of the material properties, it results in FOS located between 1 to 1.3. Therefore, design the mine slope using mean values appears to be a safe decision. And next, Habib will give us the risk about the slope design.
The excavation of the open pit mine poses several key risks that should be taken into consideration. One of them is there might be slope failure due to overestimation of material properties. As you know, might be high rainfall event or seismic event. There could also be dewatering that might lower the neighboring levels of the rivers or bore wells or aquifers. There could also be improper disposal of the mine water waste, and that could contaminate the nearby groundwater. Our design also does not account for any working space or construction vehicle road access. In the next figure, in the figure over here, you can see additional factors that could affect the slope stability. So to mitigate all those risks, we suggest that during the exploration phase, we should drill closer spaced boreholes and carry out more rock strength tests to reduce the COV for cohesion and friction angle. We also suggest to carry out daily visual inspections of the slope to monitor for signs of cracking or instability. We highly recommend installing a laser GPS technology if it's needed. Another solution is to install a warning system device at the site to detect potential threats. And to mitigate instability due to seismic events, we suggest to improve drainage along the upper and lower portions of the slope. To monitor the groundwater levels, we would need to drill water monitoring wells in between the mine site and the nearby rivers, aquifers, bore wells, whatever you're looking to look at. We suggest to plan an appropriate treatment process for the wastewater prior to ground infiltration. And if proper working space and vehicle access is required, then we can redesign the slope to add some benches. Thank you so much for your attention. And if you have any questions, we'd like to answer them.
Okay, thank you very much. So I think right now we can start with the questions by the judging panel. I don't know if they have any question, so please feel free to ask the questions for the team.
Yes, it's Emmanuel de Tournay here. So thank you for the presentation. I would like to ask you the question about the probability of failure. You decide to go through a sensitivity analysis, no? As calculating the factor of safety as a function of the parameters. Could you tell us how you translate that into a probability to failure? Because that was one of the criteria that was expected, that it was 5% probability to failure. So can you elaborate a little bit on that?
Yeah, so what we did here was at the beginning we designed the slope according to the mean values in order to be in the middle of all the possible factors. So then what we did, we took the COV values and generated the different possibility that may exist for these parameters. We did the sensitivity analysis changing a parameter at once. So according to the possibility of these parameters occurring in real life, and then we calculated the factor of stability according to that value. So the sensitivity analysis have been done on one increment of one value at a time.
And I just wanted to elaborate on that. Our design, like Ahmed said, was based on meeting one of the criteria, which was to have a factor of safety of greater than 1.3. And the other criteria was to do the probability of, address the probability of failure. So we did not go into too much detail in calculating a probability of failure. Instead, we chose to do this type of sensitivity analysis rather than try and calculate a probability of failure.
Maybe I can ask just a quick clarification. So when you do the analysis, are you assuming that the failure surface is above or below the groundwater, the phreatic surface?
I think, let's take a look. I think when we look at it here, I think the failure surface is going through the groundwater table. We had to meet the criteria that the income equals the cost. If we had made the groundwater table, if we could make the groundwater table the way we wanted to make it, we would have made it a lot, we would have dewatered a lot more. And then the failure surface would not be cutting through the groundwater table. And that's usually the scenario that we'd want to have. But I guess we were cutting it very close using this analysis. And actually, I'm not quite sure how this particular program tells us how we can get any information about where the failure surface is. I mean, it just shows us a factor of safety and it shows us the colors. And I'm assuming the failure surface will occur somewhere here. I can kind of assume where it comes out at the top, and definitely it'll probably come out at the bottom. But yeah, I mean, it's just a model. But yeah, to answer your question, I think the failure surface does cut through the groundwater table.
Okay, thank you.
Okay, so do we have any other questions by the judges?
Yeah, one more, please. You talked about how you could mitigate the risks, and one of the things that you described was having a lot more boreholes. Well, having a lot more boreholes can be very expensive, of course. So had you given any consideration to doing things down those boreholes that you already have with regards to mitigation? You know, it could be taking extra measurements down the boreholes, doing geophysics down the boreholes, etc. Do you have any comments on that?
Yeah, I guess if it was in an area that what you would be expecting seismic events, it would be important to do, I mean, I'm not sure what they're called, but doing some sort of test that would test the, you know, how the rock would move down the boreholes. I mean, if it's mostly rock, we would be just taking rock samples. So you could take the rock out and then test the strength while it's out of the ground. But doing in situ tests would be important too. I mean, if we were considering the groundwater flow, then we could do some sort of groundwater flow measurements. Not sure if it's possible to do it at depths that are that deep, but that would be something interesting to do as well, to see how fast is the water going to flow, how much water do we have to dewater to get it to this level for this long. That would be something important because that costs money too. But yeah, drilling more boreholes does cost more money, and I guess if it's only to test the rock strength, then maybe it's not necessary unless we decide to do these extra tests down the hole. So yeah, that's a good point.
Yeah, we also understand that increasing the doing more boreholes would increase the cost. However, according to the problem statement, we had a fixed value of dewatering, and we made it equal to the income. So our focus was to try to find the deepest depth that we can reach to, and make sure that the income equals the cost. So we didn't take the other risks mitigation into consideration because we had a factor of safety of 1.3, more than 1.3.
No, I understand. Thank you very much.
Hello, just for you to know, we are 17 minutes. So, Christian,
Okay.
do we leave another question or move?
I think, thank you so much for your presentation. So I would like to introduce the second team. So we can start with the Geotechnical Engineering Peruvian Advisory from Universidad Nacional de Ingeniería. Welcome.
Good morning, members of the jury, contestant colleagues, and general public. My name is Rubén Romero Maima, and I am in charge of representing to the Geotechnical Engineering Peruvian Advisory UNI-Peru team to explain our solution to the proposed problem. Well, the exposition has this outline. Okay. Problem definition. The problem consisted of a horizontal and stratified geological model with a vertical ore body of 100 meters width. For simplicity, it was assumed that all geological materials are infinite in length. The rock mass properties, such as the cohesion, friction angle, among others, were part of the problem, and they are summarized in this table. The problem requires that the maximum pit depth is calculated so that the benefit equals the total cost. To solve this problem, two constraints must be considered. The first one deals with the acceptance criteria for the geotechnical assessment, which requires a minimum factor of safety of 1.3 and a maximum probability of failure of 5%. The second constraint takes into account the ore value as well as the excavation and the watering costs. Okay, approach and methodology. The methodology that we followed consisted of three main steps. First, the results of the financial analysis were plotted as an economic envelope. This is shown as a red curve in this figure. This curve represents a function of all the break-even points for a set of slope height and the slope angle values. Second, a function that represents a constant factor of safety of 1.3 with various combinations of slope height and the slope angle was obtained. And this is shown as a blue curve in this figure. Third, the intersection point of these two curves is found. This point will give us a combination of pit height and the slope angle values, which are later assessed probabilistically. If the probability of failure results in a value less than 5%, then the slope design at this point meets both geotechnical and financial constraints. The two curves limit 4 areas with different properties of profitability and stability. Our zone of analysis is a zone 3. The main assumptions for our analysis are related to the hydrogeological and geotechnical conditions. For hydrogeological, the groundwater condition is in a steady state, and the water table is at the ground surface. For the geotechnical assessment, a bidimensional 2D analysis was conducted. Okay, the financial analysis. For the financial analysis, we use the concept of instantaneous stripping ratio, which calculates the cost and benefit of increasing the pit floor depth by an additional bench height delta H here. For our analysis, we used a delta H value equal to 10 meters. So we first calculated the benefit by taking the volume of ore multiplied by the ore value. Likewise, we calculated the total cost of mining due to excavation and dewatering following the expressions shown in here. By making the benefit equal to the cost, and by rearranging the terms of the equation, we found an instantaneous stripping ratio equal to 17 divided by 3. We then expressed the stripping ratio in terms of the area of ore and versus the area of waste, relating the slope height, the pit floor width, and the overall slope angle, as shown in this mathematical expression. This relationship was then plotted in a depth versus angle graph. By considering different values of pit floor width. Finally, the one with a pit floor width of 40 meters was selected as the most appropriate due to operational efficiency, and also it maximizes the height. Okay. Stability analysis deterministic. For the geotechnical assessment, we carry out a slope stability analysis at the overall global scale. We used a bidimensional 2D plane strain model in the flag slope software. First, we considered a deterministic analysis using the average values of the rock mass properties, and we then derived different combinations of slope height and slope angle for a constant factor of safety. Okay, in this figure shows the results of the analysis where the economic envelope is also plotted. The intersection of the economic envelope with the different factors of safety curves represent a possible answer to the problem. And from this figure, the maximum pit height is 290 meters with a slope angle of 43.3 degrees. Okay, stability analysis, probabilistics. To validate the previous results, a probabilistic analysis was conducted to complement the deterministic approach. We followed the response surface method proposed by Stephen to account for the variability in rock mass properties. We assumed a normal distribution for all strength parameters such as cohesion and friction angle by considering their mean and standard deviation. From the results, we can see that only the cohesion and friction angle of material number 2 has influence in this material number 2 on the resulting factor of safety, while the other parameters have no effect, which can be observed at these horizontal lines. And then we use the Monte Carlo sampling technique to run 10,000 iterations and obtained a probability of failure different to each height and slope, like this. And so the most appropriate is this because the probability of failure is 4.8%, which is lower than the maximum allowed. Okay, results and potential risk. As a conclusion, the results of our cost and benefit and deterministic and probabilistic analysis, we can state that the slope design that complies with both the financial and geotechnical requirements is one with a height of 270 meters and an angle of 41.3 degrees. The potential risks are the next. Material number 1 is the most unstable. As a consequence, the localization of failure here and a solution is to consider an overall potential failure. Other is the no information about the type of distributions. As a consequence, the variation of probability of failure, and a solution, the collection of more data to know it. Other is the earthquake occurrence. As a consequence, the failure by a seismic movement, and a solution, the seismic analysis, like this. Other is the water table presence. As a consequence, the factor of safety diminution, and the solution, the dewatering campaigns. Other is the no confirmation of steady state. As a consequence, the reduction of factor of safety and increase of probability of failure, and the solution, the piezometers. The last is the no information about the structural characteristics. As a consequence, a bench scale failure, and the solution, a mapping campaign. Well, okay, we want to thank the sponsors of this student competition, both Itasca Consulting Group and the University of Kentucky, for hosting this event. We would also like to express our gratitude to our advisor, Mr. Christian Obregón, for his patience and dedication throughout this process. And last but not least, a special thanks to our families for their continued support during the last weeks of this student contest. Okay, so that would be the end of my presentation, and thank you very much for your attention.
Okay, thank you very much, Ruben. So I think we can proceed with the questions.
Maybe I can start again. Hello, thank you for a very nice presentation. Can you give us a bit of detail on the Monte Carlo simulation? I mean, how did you do it? How many samples did you take? And how many realization did you take to obtain this probability distribution of the FOS?
For the Monte Carlo simulation, yes, in general, we considered these variables, the 3 most important, and in general, we used the Monte Carlo simulation to construct this graphic, and using these graphics to obtain the probability of failure. And we considered the first response that was 290 meters only with a deterministic, but the probability of failure doesn't complain the constraint of 5%. So this is the first that complies this percent.
Yeah, I was asking how many realization did you do for the Monte Carlo simulation?
Okay, we realized this Monte Carlo simulation in the software risk. Some less calculus we did in Excel, but all the process was did in the software risk to obtain these graphics and obtain the probability of failure.
But you don't, yeah, I don't know that software. But do you recalculate the? I mean, can you tell us a bit how this risk software works? I mean, I don't think that as I understand it, that you recalculate each time for each realization of the parameters, that you recalculate the failure mode, no? Or do you?
The failure mode or failure surface.
Yes, I mean, do you calculate for each realization? Do you recalculate the failure mode?
No, the failure modes or failure surface in the case of the probabilistic was assumed as the same of the slack slope because we variated some values and some was controlled in the slack slope software.
Okay. Thanks.
Okay, thank you very much.
I have a question, if I may.
Okay.
One of your risks was that the water would be present at all times, and yet your analysis shows it present at all times. So I'm wondering, you've taken the very, very worst case. Did you consider lowering the water table through pumping at cost and creating a water table that was not at the surface of the current pit?
Okay, the question was about the water table. Okay, so in general, we consider the water table is in this position, was at the ground surface as I said at the start of the presentation.
Do you have any sense of how much your answer would change if you varied that reasonably and lowered it through some means of pumping or drainage?
Yes, maybe is if we consider it to do lower the water table, maybe the result could vary significantly. But in general, we consider it to use this water surface is along all the ground surface of the slope.
Okay, thank you.
Okay. So thank you very much, Ruben, for your presentation. To keep on schedule, I think we need to move on with the third team. So thank you very much. So I would like to welcome LMR Consulting from Laval University.
Okay, so hi everyone. Antoine and me, Christopher, are here to present to you the open pit slope design and rock stability analysis of your mine project. So this is the presentation plan. So here the LMR Consulting was contracted by the ARMA-SDC team to determine the maximum mining depth of an open pit by proposing an overall slope design respecting both rentability and stability criteria for a preliminary economic assessment of this mine project. So the economic design acceptance criteria is set to the total income from the mine ore must equal the total operating cost. So a profit of 0, as you can see here. And for the slope stability analysis, must respect factor of safety greater than 1.3 on a deterministic approach, and both for probability of failure smaller than 1.5 and the mean factor of safety greater than 1.3 have to be respected on the probabilistic approach. And for the slope design process used by the team, as you can see on the figure just there, the rock mass properties of the 3 main geological unit and the groundwater condition data were provided by the clients. So a geotechnical model was constructed based on those data. The structural data were not provided. Therefore, the failure mode controlled by structures have been discarded, like planar, wedge, and toppling. So circular rock mass failure at the overall slope scale has been identified as the critical failure mode. So the overall design, overall slope design is an iterative process where the optimal mining depth slope design being in the respect of the economic design criteria and the slope stability analysis. So the slope stability analysis of the proposed design was achieved by numerical 2D finite element analysis implementing the shear strain reduction technique on the deterministic and a probabilistic approach. The deterministic approach, based on the mean rock mass properties, allow calculating a factor of safety using the 2D numerical modeling code flag slope. For the probability of failure and the mean factor of safety was calculating using a Monte Carlo probabilistic approach using statistical distribution of the rock mass shear strain parameters. The 2D numerical modeling code RS2 was used for the probabilistic approach, and the results were compared with the flag slope for the deterministic factor of safety.
So here you have the geological model of the situation, which represent the 3 geological units. The rock mass is divided in 3 different lithologies, which are unknown. Each rock mass have a specific width with a 0 degree dip, which means that they extend horizontally. The ore body in red on figure 3 is infinite in length, is 100 meters wide, and extends vertically downward from the surface. The initial groundwater is at the surface, as you can see with the blue piezometric line on the top of the figure 3. About the geotechnical parameters, the information was given by the ARMA team. The more Coulomb failure criteria was used to characterize the rock mass. Table 1 up here shows different parameters for each lithology, which are depth, density, porosity, friction angle, dilation angle, cohesion, and tension. Table 2 down there shows the different parameters used in the Monte Carlo statistical simulation in RS2 according to the coefficient of variation presented in the right column right here. Quickly, it was possible to see that each lithology could not be characterized by the same angle on the general slope, because of their properties without being unoptimized or being unstable. About the hydrogeological parameters, most of the information was also given by the ARMA design team. The initial groundwater level is at the surface, and there are no recharge nor groundwater flow. All the water is contained in the porosity of the rock, and the saturation below the phreatic surface is at 100%. The water pressure below the phreatic surface is considered hydrostatic, which means that the water pressure increases as the depth also increases. With all this information, because there is no precise way to input a pumped water table, and because there was no information about pumping wells or drain, and for conservative reason, the team decided to design the pit with a fully saturated slope, meaning that the phreatic surface will follow the topography, as you can see with the blue line here. In reality, this will not be the case because of evidently pumping wells and drains. For the recommended overall slope design, an iterative method was used. The iterative workflow was about the balance between the stability criteria, which are factor of safety and probability of failure, and the economic one, which is the rentability threshold. Through this iterative process, an overall slope design that meets the 3 criteria was obtained. This overall slope design is presented here on figure 5, with a total depth of 440 meters and an average slope of 35 degrees, with each rock mass unit having a different slope angle because of their geotechnical properties, especially the friction angle and the cohesion. Top left here present the whole slope, and the 3 other windows present each section of the slope as represented by the arrows. As for the financial analysis, 3 cost considerations presented in table 3 were used. The first one is the revenue from the ore by volume. Then we have the cost excavation of the waste and the ore itself. And then we have the dewatering cost by volume of water. The volume of water was estimated by the volume of rock excavated, the porosity, and the saturation of the rock. The economic criteria stipulated that the total income from the ore being mined must equal the total cost of the project, which are the excavation cost and the dewatering cost. Also, a 10-meter margin was used. The economic analysis shows that for the geometry of the design presented before, this rentability threshold will be achieved at a pit depth between 440 and 430 meters with a stripe ratio of 5.67. Table 4 right here shows that the profit sign shift between these two depths, which confirms that the economic criteria was met. With a design of 440 meter, the 10-meter margin is also respected. And for the overall slope stability analysis, two software were used, like Christopher said. First, FlagSlope was used alongside with RS2 from Rock Science. RS2 used a Monte Carlo simulation of 20 iterations, which could give a factor of safety, but also a probability of failure for the probabilistic approach, which FlagSlope could not give because of its deterministic nature. The main difference is that RS2 has some built-in options for a probabilistic approach. Table 5 here present the result for the analysis of the recommended overall slope design. As we can see, all the stability criteria were met. Figure 6 and 7 right here present the rupture surface and of the analysis, which represent the maximum shear strength failure surface of a deep circular rock mass rupture. On the left here, we have the analysis for rock slope and for FlagSlope, sorry, and on the right, we have RS2. FlagSlope used a coarse mesh grid and RS2 used a 300 mesh grid.
So for the risk assessment and mitigation measures, the main risk of this work concerns the rock mass failure identified as the critical failure mode. Several slope design issues have to be considered with the proposed slope design. Geology, discontinuities, geotechnical parameters, and seismicity have to be investigated with the drilling campaign, structural mapping, laboratory tests, and some mapping of the geographical investigation. Those information are required to design the geometry of the slope at the bench and the interim scales. The main issue and the principal instability factor identified by the team is the groundwater condition. So a better understanding of the hydrogeology could improve the slope design. By implementing underwater techniques like you can see on this figure, the water table could be folded down below the pit floor, which could lead to an increase of the slope stability, the optimal mining depth, and the overall slope angle for the same economic criteria. To achieve this gain in stability, you can vertical, peripheral, or in-pit dewatering wells, horizontal drains, or joint cementation, if possible, could be used in the pit to manage the groundwater condition. So a slope stability analysis on an optimized slope design configuration, assuming an operational water table, as you can see here on the figure 11, leads to an optimal mining depth of 640 meters, which meets both rentability criteria at the 10 meters margin and the stability criteria, as Antoine explained the methodology. So for closure, the proposed conservative design considering a fully saturated slope leads to an optimal mining depth of 440 meters. By implementing a mine dewatering system, the optimal mining depth could be improved to 640 meters. To confirm this affirmation, further investigation on geology, structures, hydrogeology, and seismicity are needed to achieve a right slope design and avoid a situation as presented in this figure, who probably a lot of people know what's happened there. So thank you for your attention, and if you have any question, we are here to answer it. Thank you.
Okay, thank you, Christopher and Antoine. We can start with the questions right now.
Okay, maybe I can start again. I have again a question about the Monte Carlo simulation. I noticed that you have n equal 20, so you have 20 realization. Is that correct?
Yeah, well, the Monte Carlo simulation was implemented directly in RS2 software. So for time-consuming reason and for the software to not crash, we use the 20 iteration. Of course, the more will be better. We could have done 100 iteration, but the software will have crashed. And we decided that for this region, 20 were enough. We will also could done it on in Excel with a random value and some standard deviation value, and then Excel could have computed many factor of safety, and then the proportion of these factors of safety under 1 will have given us the probability of failure. But we decided that with RS2 and linear rotation, it was we felt comfortable with that.
So the parameters are random variables, the cohesion and the friction angle. I don't remember when I read your report, are you limiting the values of those parameters to plus and minus sigma from the mean? Or okay, so
yes.
Do you think that the fact that you did that, does that affect somehow the probability to fail?
Yeah.
Well,
yes.
You can go, Christopher.
But yeah, we used 2 sigma to do the boundaries, but we know that with the coefficient of variation for I don't remember, it was the cohesion, we used 2, because if we were using 3, but we will be at 0 or something, so we decided to use 2. We know it's less conservative. We probably use a cohesion of 0, but yeah, we used 2 sigma, and we think it was right to use it at this moment for.
Okay, so you used 2 sigma and not 1 sigma. So it was my you used 2 sigma.
We used 2 sigma.
Okay.
We wanted to use 3, but with 3 it was too extended. So we were not.
The coefficient of variation is very large on the cohesion. It's 0.4, so it's
and the software was crashing when we inputted 3 sigma, so we felt comfortable with 2.
Exactly.
Negative value. That's what probably the reason.
Yeah, exactly.
All right, thank you.
There is other question?
Hello, can I ask a question?
Yeah.
Hello, Anton and Christopher. Can you please explain why you use this axisymmetric model when you do the slope design, not the whole model, as you use half of the model to do the stability analysis?
So you're asking why we analyze just one slope and not the other slope?
Yeah. Have you compared this one side slope with the whole model with 2 sides? Have you compared these 2 models?
Yes, but we felt that the result will be the same as the bottom pit depth width was large enough that the 2 of the 2 circular rupture will not come with each other, because we assumed a down pit width larger than 100 meter for operational reason, like distance safety and for the operation and the blast and the truck haulage. So we felt comfortable with just analyzing just one slope, but we absolutely did the modulation with the 2 slope, and the results were absolutely the same.
And we restricted the model, as I don't know if I can. Do you see the camera and everything? I will change the place. Just give me a second. If I show you the. Oh, we restricted just here. So logically, if there's this part will force light on this part, so probably we've seen that it was mostly here. The shear strength was greater here, but we had the same shape of circular surface. So that's why we choose only one side, and it was enough, and it was less time-consuming computation to use this methodology.
Oh, thank you. And from the left side in the central line, I can see that you set the boundary condition here, right?
Where?
Did you?
Here?
The left, no, the right picture, the left boundary.
Yep, the left boundary here.
Do you set any boundary condition here?
Yep, we fixed the point just there. We fixed it, so because we consider there's another slope just there, so the slope will not. I don't know how to say that.
Oh, the third charge.
There's a bit like a wall, so we fixed there to have only this part as the problematic to have this circular because if we're not fixing there, the computation will consider there's a movement allowed to go further there, but there's another slope just there. So that's why we fixed it.
Yeah. Okay, thank you.
So I would like to jump in here. We are at 16 minutes right now, so thank you very much for your presentation. As our schedule is very tight, I think we need to limit the questions just for the judging panel. All right. So I would like to start introducing stabilizers from India, from IIT Dhamnbad. So welcome, and you can start sharing your screen.
Good day to all the judges, fellow finalists, and the attendees. We Team Stabilizers are a bunch of undergraduates from IIT Dhanbad, India, and here is our solution for the ARMA-SDC 2021 problem. The problem statement gave us some superficial data about the rock mass properties and the likes of coefficient of variation, costs, values, value of 4, and other data. Using this data, we had to find the maximum depth to the nearest 10 meter under some constraint. The main challenge was to equalize the income from the ore and the total costs incurred. And some other safety criteria were that the FOS should be greater than 1.3 or the probability of failure should be less than 5%. We use a flat slope software, and for the probabilistic analysis, we use a Monte Carlo simulation. These are some initial assumptions that we took. We took no benches, and the model that we took had 3 slope segments. And the analysis was completely 2-dimensional. For the phreatic surface, we assumed that the D by H ratio, D means from the pit toe to the distance, horizontal distance, and the total height to be 2.5 according to some analysis. And the amount of dewatering is the total amount of water in the porosity above this phreatic surface. There's a short video to show the movement of phreatic surface as we excavate. It moves parallelly, maintaining the ratio of 2.5. Initial state, we assume the groundwater to be at the ground surface, then maintaining the ratio of 2.5 parallelly, joining the toe, the phreatic surface moves down. The overall approach started with a financial equation that included all the volume calculations and the cost analysis. And using that, we found out the depth for each and every optimization. We performed various trials, started with finding an ultimate pit for an FOS in the vicinity of 1.3. And then we carried out Monte Carlo simulation just to find out that this model had a probability of failure greater than 14%. In order to reduce that, we stepped up the FOS by in the steps of 0.1 and finally settled with a model of FOS 1.5, which has a probability of failure less than 5%. There is an overview of the financial equation that we used, and here is a pit design. 3 slope segments. This is the volume of excavation. The volume of dewatering is the volume of water above this phreatic surface. This part gives the excavation volume calculation, dewatering volume calculation, volume of ore, which is here, as we took the base to be 100 meters, exactly the width of ore. And this is the cost analysis where we equate the revenue to the total costs, finding the quadratic equation, which on solving would give a positive root, which would give us the value of x, that is depth beyond 300 meters. Estimating the slope angles, just to make it less time consuming, we first wanted to make a reference table without using the phreatic surface in the steps of 5 and 10 degrees. We checked the stability of each and every layer after every optimization and stepped it up by 5 degrees and 10 degrees. This was the table that we found out, starting with the friction angles that were given and the pit depth according to the financial analysis calculation. We got the FOS this. After incrementing 5 degrees and 10 degrees every time, this was the table that we got, and we chose this serial number 6 of the reference table to move forward. This theta1, theta2, and theta3 are correspondingly these angles of the slopes. Now coming with the phreatic surface, as we said, we took the DYH ratio of 2.5. The first angles that we used are from the serial 6 from reference table that I showed you just now. And then we run a few models with medium mesh and fine mesh just to find out that difference between both comes in the range of 0.1 to 0.3. Several thumb rules that we followed, similar to the previous case, just here that the optimization was done with a variation of 1 to 2 degrees. Starting with the previous value that we took there, as we added the phreatic surface, therefore is decreased from 1.35 to these values. And this is the angle slope values that we finalized because of fine mesh gives us an FOS of 1.303. This was a plot for this, showing the maximum shear strain line. Now coming to the Monte Carlo simulation, we generated random numbers. The whole Monte Carlo simulation is based on standard normal probability curve and conversion of any normal probability curve into a standard normal probability curve. That means mean 0 and standard deviation 1. We generated random values and assumed that these are the cumulative probabilities of an imaginary number z on a standard normal probability curve's horizontal axis. This is a sample part of the analysis that we did in Excel. We generated random values, assumed those to be the cumulative probability. Now corresponding to those, using this equation in Excel, we found out the z values. Using the z values, and as we were given the coefficient of variation which helped at finding standard deviation from the mean values, as you can see here for all the three, cohesion, friction value, and tension. We use these for all the three layers and the z value to find random values for cohesion, friction value, and tension by using mean of this layer cohesion plus z into standard deviation of this layer cohesion, similarly for all the three. Using these values of CFT, we found out FOS for various sample sets for the model that we decided. Using these FOSs, we found the mean value of that and the standard deviation value of that. Now we have to find the cumulative probability of FOS falling below 1. So we converted this into a z value for a standard normal probability curve that came out to be minus 1.04, for which the corresponding cumulative probability of failure is 0.147, that is 14.7%. And that came to a shock. So for reducing the probability of failure, we stepped up our FOS in the steps of 0.1 and 0.1. For this, in the similar way, we did optimization for 2 more slopes just to make it less time consuming. We made a model for FOS 1.4. We made a model for FOS 1.5 with these angles and this depth from the financial equation, giving us this final Monte Carlo simulation sample of Monte Carlo simulation with FOSs for 1.4 and 1.5, giving us a probability of failure of 6.52% for 1.4 model and 2.73% for the 1.5 model. As a 1.5 model was below the 5% probability of failure, there is a plot for this. There is a maximum shear strain part, and there is a tension crack here for which we will be talking about. There is a final result of Monte Carlo simulation, and these two are very near to 5%. And the depths are 394 meters and 410 meters, which gives us an estimate that 5% probability of failure would lie somewhere in the range of 400 to 405 meters. Thus, the 394 meters model is in the vicinity of 10 meters of this range. Thus, we present the model with FOS 1.502 as a final model, considering the probability of failure is less than 5%. These are some risks associated with the model. Water bearing joints, if any, can cause stability issues, and zero recharge condition was given. But in case if there is a recharge, there will be accumulation at the pit bottom, and dewatering that will cost us more and in further compromise us with the pit depth that we can go. The final design also has a tension crack, but to our rescue, the phreatic surface is just going below the crack and not filling it. But in case if there is a recharge and the crack fills, there will be a potential instability. Steeper slopes, like the slope of slope 2, which went to 60 degrees plus, would cause less resistance to falling rocks, which would speed up and cause potential damage. Rock stability at the convex slope of the pit is might be unstable, and if any discontinuity is present, they would cause potential failures. Crushing these risks and throwing away and adding some mitigations. To deal with water-bearing joints, we need to intersect the joint and drain out the water from time to time. In case of recharge, to reduce the water filled in the pit bottom, we can make the top of the pit a bit sloping out by, so that whatever water falls at the top goes outward and does not fall into the pit and accumulate, increasing the dewatering costs. Continuous monitoring can prohibit any failure or will make us be ready for that. And making benches would make it more stable in case if needed. Making some catches would reduce damage due to rock falls as it would slow it down. Convex slopes might cause instability, but constant monitoring would help us mitigate that. Here ends our presentation for the final solution. Thank you, Itasca and ARMA student chapters, for giving this wonderful learning opportunity.
Okay, thank you very much. We can proceed with the questions, please.
I can start perhaps. Can you clarify how you incorporated the pore pressure into the results?
We included the pore pressure in the flat slope software directly. There was an option to include the percentage of porosity, where we can fill the water under the phreatic surface. Like we created a phreatic surface in this line. So below this line, the whole porosity was filled with water. Thus, the phreatic pore pressure was directly considered by the software in giving the FOS.
Okay, thanks.
Do we have any other question by the judging panel?
Yeah, just a quick question about, so you have different slope, for each layer. Did you consider the possibility, I'm assuming that you have considered the possibility of local failure? For example, the top layer is very weak, no? Did you observe some slope stability which is restricted to the top layer?
Yes, for the top layer, while we were doing the optimization and analysis in Flaxpo, we found out that in somewhere in the range of 32 degrees and 33 degrees, if we make it more steeper than that, the FOS was falling drastically. So we tried to keep it in the vicinity of that, as you can see in our models, 36 degree, not much steeper, 33 and 30 degrees here. Going more steeper was decreasing the FOS drastically.
But that was for the deep-seated failure surface. I'm just wondering if you observe, when you were playing with the parameters, did you observe slope failure limited to the top layer? I'm just wondering.
Yeah, it happens sometimes. When we did, there were cases where the failure just happened in the top surface and both the bottom surface was stable. In those cases, we tried to make the top layer more flatter and distribute the stress in the other layers. That's why you can find our final models to having maximum shear strain distributed all over.
Okay. Thank you very much.
Thank you.
Okay. So thank you, Amar, for your presentation. It was very interesting. So now I think we can welcome Manic Miners from the University of Belgrade.
Good morning, everybody. I send you regards and best wishes from Serbia and Manic Miners team. I will strictly get to the point because time I have for this presentation is limited. In this presentation, I will represent you our solution with main points of our workflow in chronological order. At first, we needed to define some initial assumptions for problem solving. As you can see on this picture, we define geological model with three materials. According to the geometry of the ore body and surrounding rock masses, we can define symmetric open pit mine geometry that is suitable for two-dimensional problem consideration. Profit for different models may be calculated and compared according to a certain constant length represented as length L in this figure. For the calculation model, we adapted that length L is 1 meter long. So we get that the volumes of materials in cubic meters are numerically equal to the areas in our 2D model for slope stability calculation. The only assumption for a groundwater level in accordance with the text of the task, considering that there is no water movement, nor we have filtration coefficients for the given materials, is that the groundwater level on each considered model is on the surface of the terrain, regardless of the shape of the model. Based on this, we adapted that the material at each point is saturated with water, and the unit weight in a saturated state is the same for all materials and equals 24.72 kilonewtons per cubic meter. Model for slope analysis has three slopes with angles defined as angle A, angle B, and angle C, as you can see on this picture. All considered angles were rounded to the whole degree, and we believe that any other precision of minutes and seconds from the engineering point of view is not acceptable and feasible in practice. Therefore, as well as for the reason that the max depth in the solution needs to be determined with 10 meters precision, the final solution was not exactly zero, but we searched for a solution that best meets design conditions of the problem with the non-negative profit. Certainly, equalizing the profit of the final solution with zero is possible by slight modification of the geometry of the adapted model with positive profit. It could be done by small increase of the amount of excavation, maintaining the stability of the model. Due to variability of some rock mass properties, we opted for a probabilistic slope analysis, and as main slope stability design criterion, we adapted that probability of failure may not exceed 5%. By performing the analysis, we realized that the probability of failure criterion is stricter than deterministic safety factor criterion. The material properties for probabilistic slope analysis were generated in the range of ±1 standard deviation from the mean value. We used two programs for slope stability calculations. It was Rock Science Slide 2 and Rock Science RS2. The differences in their possibilities that matters in this task are given in this table. Slide has possibility to calculate only with elastic materials with predefined shape of failure surface by limit equilibrium method, but with time of calculation that is much less than time for calculation needed with RS2. RS2 has possibilities to calculate with all parameters of materials given in this task, using finite element method for calculations, and it is much more accurate than slide 2. The results of analysis in slide 2 gave us the range of values for angles and depths that we used for analysis using RS2 program, and by that we spent much less time than we could spend using only RS2 for calculations. Based on this, we defined an algorithm for further analysis. Cost analysis aimed to determine comparative profit in United States dollars per meter length of an open pit mine. It was simple, and in this slide you can see the model for calculation and how we defined profit. Analysis in slide 2 were performed using Bishop and Morgenstern-Price methods. The results of these analyses gave us the range of depths for further steps that led us to the final solution. For depth of 300 meters, we got satisfactory results for stability of the model with slope angles of 23 and 45 degrees. So we used them to define models for our first analysis in RS2. On this slide, you can see the output from slide 2 program for model with depth of 300 meters and with slope angles 23 and 45 degrees. Based on results of these analysis in slide 2, we also got a diagram profit depth and made a conclusion that our solution can be expected in this range, 360 to 380 meters of depth. In the next step, we used the RS2 program and finite elements method to determine slope angles that gave satisfactory results at the depth of 300 meters. Two combinations of angles gave stable slopes. We use these values to define sets of angles A and B as shown on this slide. Our estimation of possible values for angle C is also shown in this slide. We programmed the generator of combinations and got all combinations of angles as triples, angle A, angle B, angle C, where angle A is element of set of A, angle B elements of B, angle C is element of set of number C. For every combination, we also calculated profit. Here you can see the output from RS2 program for a model with depth of 300 meters and with slope angles 21 and 43 degrees. In this table is presented 10 combinations with minimal non-negative profit. The model with angles 18, 41, and 26, calculated with 3,000 finite elements, gave satisfactory results with probability of failure 4.67%. This solution was also optimal from the point of profit view, considering the initial assumption that profit should be approximately 0. On this slide, you can see the output from RS2 program for our final solution at depth of 360 meters. Based on results at 360 meters of depth, we use these results to define sets of angles for analyzing models with depth of 370 meters, and we got as a result that profits for all combinations at this depth are less than 0. That's why we adapted solution at 360 meters as a final solution. For the performed analysis, we used uniform mesh type with triangular finite element with 6 nodes. From several analyses, it was concluded that the sensitivity of the results for the probability of failure to the change in the number of finite elements is very high. With the enlargement of number of finite elements, accuracy of the calculations increases, but also the time required to perform the calculations increases. The number of finite elements that we used for all calculations was 3,000. That number was determined considering our personal computer processing capabilities to give the results of our analysis in a reasonably short time. Although we are aware of the need for calculation with a larger number of finite elements. For example, this model with depth of 370 meters has probability of failure less than 5% if we calculate it with 1,000 finite elements. But it is shown by this analysis that it cannot be a reliable result. The problem of dependency of results for probability of failure for increasing number of finite elements should be further analyzed in detail. We also did not have any data about structural properties of rock masses, position of the open pit mine, and seismic properties of that area. By including these analyses in the consideration of the problem, we would certainly get higher results for probability of failure. Those are the risks for this solution, and we can mitigate them only by getting more data for the material properties and open pit mine area and including it to our calculation of the slope stability. The open mine surrounding area should also be taken into consideration with an analysis of the possible impacts of some subsidence, especially if there are any surrounding objects. I will end my presentation here and thank you for your attention. I'm open for your questions.
Thank you. Thank you very much. So we can start right now with the questions, judges.
Can you elaborate a little bit on the financial analysis? You know, what are the equation behind? What are the equation behind the analysis? Yes.
As I already said, the geometry of the open pit mine is such that we can consider it as a two-dimensional problem, and we define this length L. We opted for the comparative profit for the length of the open pit mine. L is equal to 1 meter. That allowed us to calculate the volumes of materials as, just let me find, to the volumes of materials as areas on this picture. It is very simple calculation because we already have values of costs and values of incomes of the or selling, and these volumes were calculated as areas on this picture. These areas are really simple. It is included triangles, as this triangle I'm showing right now. This is rectangular, and that area was the volume of 1 meter of length of open mine pit. The water table was at the surface of the terrain, and it was very simple to find the corresponding costs.
Does it matter if you take L equal 1 meter? No. Why do you choose that?
Because of that, if we want to for this cross section, if we want to calculate the volumes of materials, we can calculate only areas of materials, and times 1 meter we got the volumes of materials.
If you had taken 10 meters,
we wanted to simplify the problem as much we could.
I'm asking you, does it matter if you took 10 meters?
No, it doesn't matter, because the profit that we calculated used only for comparison between various models that we examined.
Okay, thank you.
Zero is if the length of an open pit mine is infinity. If we get a zero for profit in 1 meter length, it is zero everywhere. But if we have a precision of depth with 10 meters and precision of angles with the whole degree, we needed to find a solution to compare the profits that are not exactly zero, but it is close to zero.
Can you clarify your assumptions about the water table, pore pressure, and how you incorporate that into your analysis? I can see the economics here, but can you just clarify how you incorporated the water table into your analysis?
When water is in question, we had in the text of this task information that there is no water flow. When we have initial condition that before our excavation, that the groundwater table, that groundwater level is on the surface of the terrain, we consider that when we start excavation and forming open mine pit, if there isn't any water flow, we will have the water remain on its place. And we consider when we have not any data about the rock masses more than we get already, that our water level only assumption in accordance with the text of the task, it is that water level is on the surface of the terrain. The pore pressure was incorporated in our model by putting the water tables in the model in the software, and it was included in calculations in RS2 software.
Okay, thanks.
Thank you.
Okay, so thank you very much for your presentation. And now I would like to introduce the last team. So we would like to welcome veteran on the board from UPN veteran Yogyakarta. You can start sharing your screen, please.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone, and good evening from Indonesia. Thanks for the time that given to us, the honorable judges and finalists. We are veteran endeavor team from UPN Veteran Yogyakarta, Indonesia. We'll presenting our ARMA study case result. 1. Problem definition. Our dimension has 100 meter for width and infinite for length and depth. Meanwhile, the acceptance criteria are safety factor more than 1.3 and probability of failure less than 5%. Economical balance should require in this analysis with solution mining operation cost equal to income. So the aim of this study case is to get an optimal geometry of slope including the depth limit and overall slope angle. And the second aim is determining the phreatic zone. Next, overview of geological model. This is the rock mass mean properties got different by the depth. So we can conclude that there are 3 layers of lithology in this geological model. And this is the overview of geological model with 2 materials. There are ore and host rock that has the same characterization based on its depth. The initial groundwater is in ground surface. So that's why we made the saturated model as the initial model. Next, overall slope, overall approach. Infinite slope is a type of slope that has an infinite length, and this analysis can use to determining the geometry of slope or mine opening by the open pit slope method. So it can be related with the aim of the study case that has infinite length and depth, also to obtain the optimal depth for the open pit method. With this assumption, two-dimension modeling can be the way to solve this study case. The guidelines for the groundwater are no recharge and no groundwater flowing. So the simulation of phreatic zone can be assumed. This phreatic zone simulation based on the Hook and Bright Act 1981 with the saturated condition and partial saturation condition. The partial saturation condition become 2H, 4H, and 8H. Probability of failure analysis use the statistical data with software slide 6.0 and use LAM analysis. The slope stability analysis use the BSOP method. The result of this probability of failure just for the properties data for concluding the optimal design and the mine acceptance criteria use the safety factor. Next, my friend.
Okay, the data from the study case was geotechnical data and general data for modeling slope. From those data, the first processing was mine plan method, modeling through graphical analysis to get the slope dimension, and then the dimension result could be running through flag and slide. From flag we can get the safety factor, meanwhile the slide can calculate the probability of failure. Comparing the result and acceptance criteria can make the conclusion from this result study case, and the main acceptance criteria that we're using in this result study case is safety factor. And the coefficient variation got from this study case for describing the variability of rock mass. And this is parameter showed an uncertainty value in a random variable. Therefore, we should change the coefficient of variation to standard deviation through this equation, because the standard deviation could represent the distribution at a random value in order to allow a minimum or maximum to be determined. And then this is the tabulation from variability data from covariance and standard deviation that classified through the depth in friction angle, cohesion, and tension. And this is the result from computing a probability failure with slide. Slope design procedure and result. The analysis to determine the geometry of slope using the infinite slope. For the range of slope height is 0 until 500 meter, and overall slope angle is 20 degree until 40 degree as commonly designed slope. Graphic analysis from MATLAB software with correlation between slope height, economical balance, and overall slope angle based on the phreatic zone condition. And this is the graphic for graphical analysis classified by the phreatic zone, and this is the for fully saturated slope. We can see the ordinate here is for the economical balance, and for the axis is for height, and the
overall slope angle drawn to non-linear curve. Therefore, to get the dimension over here, just plot the economical balance here to get until for non-linear curve, and then we can get the down vertically to get the height. And then this is for the partial saturated 2H. This is for 4H, and this is for 4H, 8H. And this is the tabulation for the slope dimension. For financial analysis, the cost for this financial analysis were our value, excavating, and dewatering costs. And the economical balance, we should to equal the income with the mining costs. And we can see the equation in this slide. And this is the table was accumulated the economical balance from geometries that we got from the graphical analysis before.
And for final design selection, this is the tabulation data from computing slope stability through slide and flag. Safety factor was the main acceptance criteria. Therefore, in every periodic zone condition have an optimal model. The optimal model was in gray rows, and we can see the slope modeling in the right side of this slide. For optimal model, the conclusion of model is the partial saturated condition into H with slope angle of 35 degrees and slope X about 350 meters. It is in the second model. This model selected because it has a maximum depth than the other model, and it's related with the infinite analysis to find the critical height from safety factor. Next slide. Risks to the proposed solution. The risks that need to be considered in the application of the model are, first, the condition of slope instability due to groundwater pressure change. Water pressure causes the effective stress and affected to the slope stability. Second, the potential for failure occurs in the upper layer. From the computing using flag in the left picture, we can see if the tension and shear from plasticity indicator cumulated in the slope phase from the ground surface until about 100 meters. The rock mass mean properties showed that the upper layer was the weakness strength in the rock mass from the friction angle, cohesion, and tension. And third, uncertainty of rock mass properties. The uncertainty from rock mass properties showed with statistical data and cold computing through probability of failure. Next slide. Risk mitigation. Number one, the pumping test or slug test is used to determine the initial groundwater condition. The initial groundwater was the main parameter as modeling the periodic zone. Number two, the horizontal drill can be a solution for the dewatering process. The horizontal drill has an easy and common application in the mining area for managing the periodic zone. Number three, the benching method can be an alternative to minimize the potential of failure. Number four, slope monitoring can be applied to anticipate failure from observing the indication of slope movement. And the last, mining design optimization in the geometry model and dewatering activities could affect the economical analysis. This is the last part of our presentation. Thank you for your attention, and we return to the moderator.
All right, so thank you very much. We can start with the questions or comments from the judging panel.
Yes, maybe if I could start. So you showed that the failure surface is restricted to the top layer in a design where you have restricted the design to be such that you have only one slope angle. I mean, wouldn't it make sense since the failure is restricted to the top layer that at least to reduce the slope angle in the top layer? Wouldn't that make sense to do that? Because you're penalizing in a sense, no? By forcing one angle.
Okay, I think it makes sense because we made the slope in overall slope angle, and And from the slide you can see here, for the plasticity yield indicated in the upper layer. So it means maybe for the managing the potential of failure here, maybe can decrease the slope here. I think makes sense for making models like this.
And maybe increase the slope angle in the lower layer. Okay, thank you. So that's
Do we have any other question or comment to the last team from the judging panel? Okay, so in that case, thank you very much for your presentation. This was the last presentation of the competition. We would like to congratulate all the participant teams for your interest and effort in this competition. So right now, I would like to, I will share my screen, and I would like to introduce Andrew Bunger, who is the incoming Vice President of the American Rock Mechanics Association, for the closing remarks. So welcome, Andrew.
Good morning, everybody. So my name's Andrew Bunger. I'm a faculty member at University of Pittsburgh. And I want to take a minute to just let that number sink in that was mentioned earlier. 40 registered teams from 29 universities, 17 countries. When Juan Jose and Christian approached ARMA about this, we said, well, let's just try it and start small and see what happens. And this is a very expansive version of starting small, really amazing. And congratulations to the teams who became finalists in such a competitive field. So congratulations to everybody here. Special recognition to Juan Jose Monsalve and Christian Cardenas for their initiative. To Lauren Lorig and David DeGagne for stepping up and really providing that guidance and mentorship and defining the problem and all that they did in order to make this go forward. Thank you too to Peter Smealy and Jim Roberts from ARMA. And I think we all are extremely appreciative, and we would raise a great round of applause for our judges if we were in person, to Antonio Bobet, Emmanuel de Tournay, Mark Dietrichs, and Paul Young for giving their time, and with their collective experience, I'm sure it's been a great experience for our students to have that input. So congratulations everybody on such a great day. So I'm really impressed at how many of our finalists are from countries where we don't have current ARMA student chapters. I do want to just give a minute of a plug for ARMA student chapters. We have ARMA student chapters in several different countries around the world. Becoming a student chapter is clearly outlined on the ARMA website. So some of you maybe have a group of students on campus and a faculty member who'd be willing to be an advisor, and that may be a next step. So certainly give that a thought, and maybe you could be the officers of the next ARMA student chapter. You can go to the next slide. With that, I want to invite everybody to the ARMA Symposium next week. Make sure to register at the website, and I want to give a particular highlight of two events if we go to the next slide. So the first is when you'll find out who won, which of course is what everybody is of course really interested to know. So the winners of today's competition plus other student competitions will be announced at Tuesday's keynote, which is taking place on Tuesday, June 22nd. So be sure and follow that in the program, and you'll be interested to be present there to see who's won this very competitive competition. And then on to the final slide that I have, which is to put in a special plug. If you have not registered for this event, I really encourage you to register and participate and spread the word about the mentor student event. This is a event taking place on June 18th, 10 to 5 U.S. Eastern Time. You can convert that to your local time. But you know, a really substantial list of individuals who are willing just to meet with students and go through question and answer sessions. I know when I've been a part of these in the past, we've covered all kinds of topics. I know students are often wrestling with industry versus academia versus national labs, their path in their career. This is a time where you've got people who have all of those different experiences represented and can give you lots of input into your career going forward. So please take full advantage of that opportunity. So again, thank you to everybody who's been involved in today. Congratulations to all the groups on a fantastic day. Stay safe and have a great symposium.
Okay, so thank you very much, Andrew, for your comments. I would like to thank you all for your participation and interest in this competition. We are looking forward to hosting future competitions every year, hosted by the American Rock Mechanics Association. Thank you all for your contributions, and we will be in touch with all the finalist teams. We hope you have a good day. Okay, so thank you very much.
Thank you.
Thank you.
Thank you, everybody. This concludes the webinar today.